Hello, welcome to The Naked Scientists with me, Chris Smith, and with Ginny Smith. Hello, Ginny.
Hi, and this week we're looking at how to protect the declining bee population. We uncovered the genes behind migraines and how the world's smallest movie was made from molecules.
Plus, we're touching up our knowledge on how the iconic St Paul's Cathedral was restored, and we'll find out how we're trying to conserve ancient and modern objects, right through from oil paintings to plastic and PVC. So there's hope for your PVC bikini yet, Ginny.
Oh, good. If you'd like to get in touch with us here at The Naked Scientist, email studio@thenakedscientist.com, tweet @nakedscientists, or find us on Facebook.
The Naked Scientists podcast is powered by ukfast.co.uk.
And joining Ginny and me for a look at what is making science news headlines this week are Laura Howes, she's from Chemistry World magazine, David Weston, who's a neuroscientist at Cambridge University, Laurie Winkles, who's from the National Physical Laboratory, and Dan Cleary, he's the deputy news editor for Science magazine. First up, this week, the European Union, the EU, announced a 2-year ban on 3 of the world's most widely used agricultural pesticides. And this is being done in the hope that it will help to preserve the declining bee population. Laura, you've actually been looking at this. So what's the story here?
So since about 2006, the number of bees has been declining quite worryingly. And that's a problem not just for people who like honey, but also for agriculture generally, because bees are pollinators. So the EU this week has decided that it's going to enact a ban on, as you say, 3 neonicotinoid insecticides or pesticides. That's going to come in December and last for 2 years right across Europe.
What are these pesticides, these neonicotinoids? What's special about them?
So they're called neonicotinoids, neo for new, and nicotinoid because they're like nicotine. So just like the addictive chemical that you get in cigarettes, but is also a poison. In fact, nicotine used to be, and I think still can be used as a pesticide. And I think there's an Agatha Christie story where nicotine is used to poison I can't remember, but some character in one of the stories.
So someone dies. Usually does happen in an Agatha Christie murder mystery.
And they use nicotine. So it's in small doses, we like nicotine, but it can actually be quite a bad poison for humans as well.
Any evidence this really is bad for bees?
There is conflicting scientific sort of evidence on both sides. Quite a lot of evidence showing that neonicotinoids confuse bees, lead them to be disorientated, things like that. However, a lot of that science has been criticised for not necessarily being accurate to what would happen in the field, and field studies haven't come up with quite the same evidence. So this is a bit controversial, but I guess it's a safer than sorry.
Is it a sound strategy? Because if they're not using 3 pesticides, does that mean that they're going to use some other kind of pesticide that may also be equally bad for bees?
Yeah, I mean, this is one of the big worries about this ban. If you stop using the neonicotinoids, they are very widely used, in part because you don't actually have to use very much of them, and you use them as seed treatments, which means you treat the seeds and then that makes the entire plant sort of give off this chemical. But it means you don't have to do quite so much spraying. If you're then going to ban these chemicals, then you're going to have to start spraying with older, more environmentally damaging pesticides.
Do they hang around in the soil as well, these neonicotinoids? So in other words, we ban them for 2 years, but is there a legacy effect that the stuff that's already there is going to stay there, at least for a while?
It might stay there for a while, but I mean, this is one of these things with all these sort of pesticides. There's always a balancing act. The other problem, of course, is that even if we do change things, then are we monitoring them well? Although a ban is going to come into force, there hasn't been much talk about actually what's going to be doing to monitor it and see what happens.
Because Ginny, also this week has surfaced some new evidence on why bee numbers might actually be nosediving the way they are.
Yes, well, this paper suggested that honey may actually be protective for the bees that produce it, and the replacement food that's often given to farmed bees may have a role to play in this drop in the bee population. So there have been lots of ideas about why the bees are declining. One of them's to do with things like the pesticides that Laura was talking about. Other people suggest it's infection by pathogens. But this new paper published in PNAS suggests it may be down to the food they're eating. So normally, bees collect pollen and nectar from flowers and they use that to produce honey. But when food's scarce, or to save money, or because they want the honey, beekeepers sometimes substitute sugar syrup for this honey. So the bees eat the sugar syrup and it's nutritionally similar. But Mayo and colleagues from the University of Illinois have shown that it actually lacks components that may be vital for the bees' survival.
Oh, really? So what did they do?
Well, they managed to extract 4 components from this honey, and they found that 3 of them increase the activation of a family of genes. Now, these genes are called cytochrome P450 oxygenases, and they're responsible for detoxifying pesticides and also metabolizing other plant chemicals in the bee diet, including honey flavonoids. So without them, it's really much harder for the bees to deal with any pesticides and poisons that they come across in the natural world.
I see where you're going. So by replacing the bees' natural food source, the honey, with this sugar syrup that doesn't have these chemicals that are in the honey, the bees don't have this stimulus to make these detoxification enzymes, or at least to the same level as they would do normally, which means they might be becoming more vulnerable to the sorts of things that you were talking about, Laura.
Absolutely, and I think this is one of the things that we really need to be aware of, is that no one really understands colony collapse disorder, which is what we call this drop in bee numbers, and it's probably actually a huge mix of different variables, so it's going to be very hard to try and untangle what's going on.
Yeah, well, what was really interesting was it actually wasn't just detoxification that these genes encode. It's also a protein that has antibacterial properties. So not having this honey has a several-fold effect, that they're not able to deal with poisons, they're less able to deal with microbes, and they might even be less able to digest their food. So it's really not having a good effect on these bees, feeding them sugar syrup.
So what's the answer then? Supplements for bees? Do we need sort of bee vitamins? Ba-boom.
Vitamin bees.
Well, possibly. I mean, if we are going to keep taking their honey, we need to at least make sure that they have these compounds, these components that make them produce the chemicals to deal with anything that we're putting into the environment that they can't otherwise deal with.
So headache for bees. You've been looking at headaches, though, David, of a different kind, migraines.
I have. So this week, a paper was published that gives us a link into the genetic cause for migraines. So a group of scientists working at the University of California in San Francisco have recently just published their data indicating that migraines could be the result of maybe just 1 or 2 single mutations in a particular gene. And this gene was initially characterised in a couple of different families around the world. And they were particularly interesting because these families suffered from severe migraines, but they also suffered from a different type of disorder called familial advanced sleep phase syndrome. And this is a sleep disorder where people are very sleepy early in the evening and they have insomnia in the early morning. So they seem to be suffering from 2 different problems. And these families in question had a mutation in a gene called casein kinase 1 delta, or CK1 delta. And this seems to be the result of, this mutation seems to be causing both of these conditions.
Do we know what the gene is doing in these people to produce both the changes to their body clock, so they have this funny evening sleepiness and getting up too early, but also this preponderance to get migraines?
Yeah, so there's increasing evidence about the role that this gene plays interacting with body clocks. So it seems to interact with several proteins that kind of regulate the body's ability to keep time. But the main aim of this paper was to look into the migraine issue. And they found that when they sort of introduced this mutation into mice, they could mimic some of the effects of human migraines. So the animals that they tested were more sensitive to heat and touch, and this is a model for kind of the sensory sensitivity that you get with migraines. They also suffered from this phenomenon called cortical spreading depression, which is this kind of excitatory wave of impulses firing in the brain, which is quite a characteristic feature of human migraines.
So it's interesting that just by fluke, these people who happen to have this funny disturbance to their sleep-wake cycle happen to also have migraines. The 2 are connected by this gene, but the gene is doing 2 different things in 2 different conditions here. Does it provide any insights, though, as to how we might be able to help people who have migraines or treat them better in future or prevent them getting migraines?
Yeah, so the really great thing from this study is that identifying a gene that really gives the symptoms of migraine, or a mutation to this gene, allows us to unlock some of the molecular details. So the paper has identified that this gene is involved in how astrocytes, particular types of brain cells, link activity in the brain to how blood vessels constrict and dilate. And the dilation of blood vessels in the brain is believed to be one of the major features of migraines. So if we can work out how we can target this gene or maybe enhance its function, then maybe we can try to treat people with migraines.
Thanks, David.
That would be great news if we can find a cure or a treatment for migraines. But Laurie, you've been looking at news about a new filter which might help clean up oil spills.
Yeah, exactly. We all saw these images of the Deepwater Horizon oil spill in 2010, and that really highlighted the need for new ways to filter and clean water. And a solution may be in hand from a group at Deakin University in Australia. They've just reported in this week's Nature Communications that they've developed a porous boron nitride nanopowder, which is actually capable of soaking up to, well, actually over 30 times its own weight in oils, organic solvents, and dyes. So some of the real issues around pollution within our water streams.
So why boron nitrate? What is it? What's special about it?
So boron nitride is first of all, it's quite cheap to produce, and unfortunately that is a big consideration. The other thing about it is that many of the existing kind of filtering materials are based on carbon. So they're based on small scale carbon structures because they're good at absorbing, they have good absorbing properties, and they have a large surface area over which to absorb these chemicals. But if we're talking about graphene, you're talking about a huge cost. So boron nitride has generally been used because it's much cheaper and it has very similar properties to those small-scale carbon structures.
Absolutely. Now, I know that boron nitride is actually what we call isoelectronic with carbon. That's because boron and nitrogen are kind of either side of carbon on the periodic table, so they share a lot of the same properties and the same structures. But I wonder whether this is really graphene. I know they say in the paper that this is white graphene, and it seems like a bit of a marketing exercise to me. What do you think?
Yeah, I have to agree with you on that, Laura. I feel like graphene almost needs to be mentioned in every materials paper at the moment, just so it can get published. But you're right, of course, it does have very similar properties. So it's kind of easier to maybe point people towards something that they may be more familiar with than something that sounds a little scary, like boron nitride.
What could you actually do with this then, practically, Laurie? How would you deploy this stuff?
So what these guys have actually done is they have sprinkled some of this powder, these layers of boron nitride with pores in them, on top of spills of oil, on top of solvents like ethanol and toluene, which are very heavily used in the kind of leather goods industry, and dyes like those that are used in the paper and textile industries. And they've just looked at how it's being absorbed. So about 1 gram of these boron nitride nanosheets can absorb up to 33 grams of impurities. So everything from those solvents right up to engine oil. And
once you've done that, Laurie, is it then got to throw it away, or can it be recycled?
Brilliantly, this stuff can actually be cleaned. So you can burn it in air and you can reuse it again and again. So once it's been used once to absorb oil, you can actually burn it in air and use it 5 more times before you need to get rid of it.
Absolutely amazing. Laurie, thanks.
So finally, Dan, you've been taking a look at Jupiter and how water's ended up somewhere it shouldn't be.
Yes, that's right. Sorry. This story starts with comet Shoemaker-Levy 9, which some listeners might remember collided with Jupiter in 1994. The first time astronomers have been able to witness 2 bodies in the solar system colliding with each other. They were then interested in what effect it was going to have on the planet. And a couple of years later, they were able to detect water in the upper atmosphere of Jupiter, which doesn't normally occur. And they were curious, did this water come from the comet? They couldn't at that time tell whether it was. There were other sources of water that could have, got into the upper atmosphere. So along comes the Herschel Space Telescope, which the European Space Agency launched in 2009, and it had much higher resolution than previous ones, and a group from France, from the Bordeaux Astrophysics Institute, pointed Herschel at Jupiter and were able to figure out that most of the water was in the southern hemisphere of Jupiter, which is where the comet hit, and the concentration peaked at 44 degrees south, which was just where the comet hit the planet. So they're confident in saying that 95% of the water that they're seeing in the upper atmosphere was from the comet.
How do you even know that there is water on Jupiter? I mean, you can't go there and take a sample.
It's from the spectrum of light that comes from the planet. And Herschel is an infrared telescope, and it is tuned to those sort of wavelengths.
OK, so They see this water and it's in roughly the same place as the comet, so they're putting two and two together and saying that it came from the comet. Can you remind me what exactly a comet's made of? Why would there be water that it could transfer?
The comets are remnants of the creation of the solar system, and people refer to them as dirty snowballs. They are largely water with other bits of rock and minerals. So they carry around a lot of water. And this result is quite interesting for theories of how the Earth came to have so much water. That's always been a bit of a mystery. We have more water than we should. And some people think it was brought to the Earth by comets. So this result supports that theory.
David?
Yeah, I was going to ask, why are we particularly interested about why Jupiter might have more water? I mean, I know it's obviously fundamental for life, so is this kind of the angle that people are interested in, or...?
I don't think it's that. I think it's because this is an event that no one has seen before, two bodies colliding with each other. And we know that early in the solar system, there were many, many more comets around, and the planets were bombarded by comets at a much higher rate than they are today. And so being able to see a comet hitting Jupiter, you can study the effect it had, what sort of damage it did to the atmosphere of Jupiter, and how the material of the comet is dispersed afterwards.
Dan, thank you very much. And thank you also to David Weston and to Laura Howes and Laurie Winklis, who joined us for the news this week. And you can find the full write-ups of those stories they were discussing and the references for them, if you'd like to follow up further, on our website at nakedscientists.com/news.
Now, you might have seen this week that researchers at the computing company IBM have entered the Guinness Book of World Records. They've created the world's smallest movie about a boy befriending and playing with an atom. But move over Helen Mirren and George Clooney. The actors in this 90-second clip are carbon monoxide molecules. Here's your quickfire science about how the film was made from Naked Scientists Elena Tay and Pete Skidmore.
The movie was made by moving carbon monoxide molecules one at a time across a copper surface.
The molecules were moved with a scanning tunneling microscope, which magnified them 100 million times. That's the equivalent of making an orange look the size of the Earth.
Scanning tunneling microscopes have a needle tip 1 atom wide, which can be very delicately controlled to scan the surface of an object.
If the needle moves close enough to a molecule, the molecule will stick to it because of the same force which makes geckos stick to walls, the van der Waals force.
The molecule can then be dragged around to any location that the researchers choose.
During this process, the molecules were kept at minus 260 degrees centigrade to make sure they stayed still and didn't vibrate due to heat.
Once moved, the molecules stayed in their new position because they formed chemical bonds with the copper atoms in the surface underneath.
The scientists then took an image of the molecules, which made up each frame of the film.
4 scientists worked for 2 weeks to make the 90-second video.
Researchers hope that in the future, laying out atoms and molecules in different configurations can be used to store data more compactly.
This will work by using the molecules to replace the zeros and ones in computer data.
And if you haven't seen the world's smallest movie yet, then you can follow the link from our website.
You're listening to The Naked Scientists with me, Ginny Smith, and with Chris Smith. In the last month, we've been hearing more and more warnings about the dangers of antibiotic resistance in bacteria. The UK's Chief Medical Officer, Dame Sally Davies, even warned that within 20 years, people could be dying from routine surgery as a result. But this week, a paper in PLOS ONE revealed how a substance found in human breast milk can make antibiotic-resistant strains sensitive to those drugs once again.
And to find out more about this, we're joined by Anders Håkansson from the University at Buffalo at the State University of New York. Hello, Anders.
Hi, nice to be with you.
And you. So tell us, first of all, what is this protein that you've discovered? What's it doing and where is it?
Well, so the protein we've discovered is present in human breast milk, and it's essentially a complex between alpha-lactalbumin, which is the most common protein in human milk, and when it attaches itself to a fatty acid, which is also prevalent in human milk, called oleic acid, a complex is made that has this activity that it can sensitize antimicrobial resistant strains of bacteria to the antibiotics that they are resistant to.
So in some way, it renders bugs that can normally grow with impunity in the presence of an antibiotic compound as sensitive again. How is it doing that?
Well, so what we know at this point is that we know that our protein is acting directly on the membrane. It binds to a pump that normally extrudes hydrogen ions. And all cells, both our cells in the body and bacteria, have a tendency to keep different concentrations of ions on either side of the membrane. And by attacking this pump, suddenly the concentrations cannot be kept up differently on each side. And when that happens, suddenly all the other ion concentrations are kind of messed up. And we get calcium and other types of ions coming into the cell that suddenly destabilizes the bacteria to the degree that suddenly now antibiotics can reach their target much more effectively.
But if you take penicillin, for example,
yes.
A lot of bacteria that are resistant to that make an enzyme that binds the penicillin molecule and stops it working. So how would this process resensitize bugs to penicillin?
That is a very good question. So what we have done at this point is we have looked at methicillin-resistant and also actually penicillin-resistant bacteria. But most of the bacteria we've looked at are more penicillin-resistant based on their ability to change their penicillin-binding proteins on the outside rather than the enzymatic activity. So but the bacteria that do have the enzyme, what seems to be happening when we add our Hamlet protein is that messing around with the ion concentrations renders the bacteria enabled to make energy. And most of these enzymes requires energy to act properly. And the other thing that seems to be happening is that the cell wall structures are changing to the degree that antibiotics have an easier way to get access to them, even though there are enzymes around that can cleave the penicillins.
So would this effect be active against a broad class of bacteria, or will it only work against some bacteria?
So at this point, we have quite good evidence that it will work against a number of different species of bacteria. So the paper that is just published was talking mostly about methicillin-resistant Staphylococcus aureus because we wanted to make a case with a bacterium that is a big clinical problem. But we've also tested E. coli. We've tested and a number of both gram-positive and gram-negative bacteria that are kind of common in clinical situations and where antibiotic resistance is a big problem. And it seems to be working on all of those.
Which is very good news. So how would you see this actually being deployed? It's a protein, so you couldn't just swallow this as a pill.
No, that's right. So if we were to swallow it, it would probably be, it's not really degraded very well, but it's not absorbed very well from the gut. So the way I foresee it at this point is that what we're pursuing at the moment is mostly topical application. So with staphylococci, we have wound infections and we have pneumonia where we can do inhalation rather than eating a pill. We also have, we could go into vancomycin-resistant enterococci or Clostridia, which also are gastrointestinal infections. And in that case, you can actually eat the protein together with the antibiotics and get an effect on the mucosal surface because this is not inside the body and in the bloodstream.
Is it safe and well tolerated?
Yes, as it's a human breast milk protein, infants are drinking it daily, and we have tested this at very high concentrations, both in animal models as well as in humans, actually, and we don't see any side effects whatsoever.
So is there not a way of making the human body make its own Hamlet protein so that you don't have to give it? You could just turn on the ability of the body to make it itself?
Well, the only problem is that this is only produced during lactation, so it's only produced in human milk. So there's no other cells that are actually producing it. So you have to, the other option would be to drink breast milk rather than making synthetic protein. And that might actually work well as well.
Anders, we'll have to leave it there, but thank you for joining us. That's Anders Harkinson from the University at Buffalo at the State University of New York. Thank you very much. If you'd like to get in touch with any questions or comments, please email studio@thenakedscientist.com, tweet @nakedscientists, or find us on Facebook.
The conservation and restoration of great art once relied only on a good eye and talent with a paintbrush. Now, though, scientists and art conservationists are working together to develop new techniques to preserve our cultural heritage.
Later in the show, we'll be investigating the conservation of oil paintings, as well as modern materials like plastics, and that's where Ginny's PVC bikini comes in. But first, in 2011, one of the most iconic buildings in the UK, that's St Paul's Cathedral, completed a 15-year, £40 million restoration project to remove centuries of London grime from its walls.
State-of-the-art techniques were required to restore the building to its former glory. And to find out more, we're joined in the studio by Oliver Carrow, who's the current Surveyor of the Fabric at St Paul's. Now, Oliver, buildings like St Paul's seem very permanent, but what actually happens to them over time?
Well, they're made of stuff. They're made of stone and wood and metal, and all of this stuff in itself, intrinsically, has a lifespan to it. But it's in an environment, and the environment can intrude on how it behaves rather aggressively. And, of course, there are many enemies to old buildings, but water is our main enemy, dirt another, and then there is the sort of the chemical soup of the environment generally and the atmosphere. But of course we mustn't forget that people are a great enemy of buildings, and they get up to mischief, they damage, but they also damage with good intentions, and we have to watch out for that too.
So what's St Paul's actually made of?
Primarily Portland stone, but much else besides, and that's a long and complicated story, and many books have been written about it.
What actually is Portland stone?
Calcium carbonate. It's seashells settled and on the seabed, compressed and made into a lovely homogeneous matrix of a very enduring and very durable stone.
But susceptible to acid attack.
Very much susceptible to acid, and it's a great irony, of course, that St Paul's Cathedral was built and funded by a tax on coal coming into London, and that coal actually not only creates acid rain but soils the cathedral. And Christopher Wren, in his own day, had the cathedral cleaned because he recognised the damage caused by coal.
How quickly does grime build up, and how thick is the stuff that gets deposited?
Well, that's an answer that science has to tell us. But one thing, old age is beautiful, and I think one mustn't sort of dodge away from that. We love things to look old, but there are incrustations on St Paul's Cathedral which are literally inches thick, and they are quite beautiful. And one mustn't ignore that. I mean, they are like frozen black waterfalls of grime, even like exquisite folded gossamer fabric. It is exquisite.
You would have thought that the dirt could be regarded as kind of an added value.
Well, it doesn't sort of play on radio, but it is something that you have to see.
So if water is bad for limestone, then how do you go about cleaning it?
Well, there are lots of methods, and in the past water has been used aggressively and literally flooding the surface of the cathedral, and back in the 1970s and 80s that was done extensively, and you get some rather nasty unintended consequences. What we do now on the outside of the cathedral, in the last programme that my predecessor Martin Stancliffe led heroically really for 25 years in fact, they used micro-abrasives, and very, very carefully, just slightly wet abrasives have been used. And then there are lots of other techniques besides. And
But you said that water was bad. Why was just washing it bad?
Okay, what happens?
Doesn't it happen every time it rains?
Stone has a skin, just like you and I. And if you literally, if you sit in the bath and scrub yourself in water, actually it's not very comfortable if you do that for too long. So exfoliation, has its demerits, but stone doesn't regrow its skin like we do. So you can actually drive water through the surface of the stone. It loses its hardness, and that then leaves sort of soft material behind. But also what can happen is you get water into the joints of the stone, which goes into the core of the wall, and the middle of the wall is lots of rubble held together with lime mortar, and you don't know where it's going then. So you have to be very, very careful.
So what kind of techniques can you use that don't involve water?
Well, on the inside of the cathedral, we used a piece of chemistry, a really quite exotic piece of chemistry, and a material called artemundit, which is actually rubber, slightly alkaline rubber, that was sprayed onto the cathedral in a very special St. Paul's formulation. And that, again, it's very beautiful the way you do it, and it stinks. But you apply it on like a poultice. You leave it for just under 24 hours, and then you can peel it off, and you can literally see the dirt peel off.
It's like this is just what you do in the beauty parlour. I mean, not that I'm speaking from experience. Maybe you, Ginny, I don't know, but I've heard that people apply these things to their skin and then sort of peel them off, and all the kind of gunge comes with it. It's sort of similar.
It's exactly like that, and there is a lovely analogy between sort of makeup and sort of health treatments and this process. But
how
I
do
think
you know
we
you're doing
like
no
to think
harm, though? I mean, that's the key thing, isn't it? I mean, you've said here it's critical to do no harm. So how do you know this isn't harming the stone?
Well, just stretching the analogy with beauty treatments, you wouldn't do something to yourself if you knew it might do you harm.
Well, people have breast implants all the time. I mean, to make a point, I mean, people do cosmetic things, and actually they do turn out to have a sting in the tail.
And they're not reversible at the end of the day. And there's a sort of, we have to enter into this world, I think, firstly with a sort of philosophical framework, and that in a sense is a branch of history of art. But I think most people will have heard of William Morris and the sort of basic intention that you don't go and muck around with old buildings because you lose something every time you do that. And in the more 20th and 21st century, we have sort of lots of charters that international charters, the Borough Charter, the ICOMOS Charter. These are perhaps a bit obscure, but they sort of try and establish a philosophical framework of why we do things to old buildings.
But when you buy, say, a touch-up kit for your car, it always says try this on a small area first.
Yes.
Do you have a small area of St Paul's that's your sort of test area when you come along with your latex mask? You think, I'll just try this here, and if it does make a bit of a mess, it's minimised the damage, rather than comprehensively doing a 40 million quid project all at once?
Well, I think some of the sort of misadventures of the past we strenuously tried to avoid in this latest campaign by doing endless trials. And there are about 10 sets of trials, all carefully reported and examined by many experts and the people who give permission for these works to establish that actually we do no harm. I think that has to be our first priority. But any intervention has some sort of long-term ramifications. So we keep an eye on things. And we also think it's very important to sort of keep records of what we did, because there's nothing worse than going back and saying, well, we think something happened here, but we don't know. And then you can't sort of track the impact of that.
So is this sort of an ongoing project now with the latex cleaning? Is this something that you will then, a bit like the Forth Bridge, you're basically starting as soon as you finish, so you just keep on going doing these peels to keep the surface clean? Or is this just something you're trying out?
No, this is now being completed, and actually one of the very bold things that the cathedral did under Martin Stancliffe is they said, if we're going to do this clean, we've got to do it all. We can't leave the cathedral half clean. That would have been awful.
Brilliant. Thanks, Oliver. That's fascinating. I'd never even thought about how you go about cleaning these buildings. I just completely passed me by.
I thought it was a scrubbing brush and a bit of warm water.
In the bath.
Yeah.
But you can actually visit a website which shows the difference that this restoration's made to St Paul's, and you can follow a link from our website to find that. This is The Naked Scientists with Chris Smith and with me, Ginny Smith. If you have any questions about art conservation or any of the other topics we've been discussing in today's show, email us at studio@thenakedscientists.com, tweet @nakedscientists, or find us on Facebook.
Buildings like St Paul's can easily stand for centuries, but what about the fragile paint that goes onto canvases? Well, earlier this week, Ginny went to the Fitzwilliam Museum in Cambridge to meet Sally Woodcock, who's currently completing her PhD at the Hamilton Kerr Institute, to find out how oil paintings age.
Today we've come to the Fitzwilliam Museum to have a chat about some of their paintings. Obviously we've got all these beautiful paintings from hundreds of years ago that we want to keep and preserve so that our children and our children's children can still look at them. But what happens to paint as it gets older?
I think you can see here in the Fitzwilliam Museum, many of the paintings will tell you that story, because paint, as it dries, it changes, but then it also changes in relation to its environment, so it will respond to change. And so you've got paintings here in the museum that show overall patterns of ageing cracks, and then specific areas of drying cracks. And then I think we're looking at an Edward Lear at the moment here, the Temple of Apollo, which has fabulous concentric spider's webs of cracks where at some point in the distant past someone has bashed it, thought nothing of it, and then 20 or 30 years later this spectacular crack pattern propagates in the paint film. And those are permanent. They are part of the history of the painting.
So what I can see here, it's a beautiful, huge painting with trees and rocks, and most of the time it looks perfectly fine. But if you get it so that the light's hitting it at a certain angle, there does seem to be a sort of ring of circles. So you think that's where someone actually bashed into the painting?
Yes, it's an impact crack, and it's likely to be where somebody bashed the back or the front, and it just allows the tension that's in the paint film to release, and you just get this crack pattern. When you look at a painting at an angle, you normally talk about looking at it in raking light, and it's one of the methods of examination we use just to be able to look at the surface, and it gives you an idea of the surface topography.
What's the difference between drying cracks and aging cracks?
Superficially, you can see a difference because drying cracks occur when the paint film is very brittle, and therefore they're rather sharp, and they normally form an overall network, often over the whole painting. Sometimes they're more prominent in certain passages of paint, but they've got sharp, angular crack patterns, and they differ from drying cracks, which occur at a much earlier stage in the painting's aging, when the painting is drying and is still quite a flexible film, and they flow slightly, so they're often rather curved at the edges. They're quite often the actual aperture of the crack is rather wider, and they often make the surface look at worst like a crocodile handbag, and they again can't be treated because they are part of the original materials of the painting, even if it wasn't the artist's intention ever for it to look like that.
So why do some of these paintings get lots of drying cracks, others get more aging cracks, and some look perfectly normal even after hundreds of years?
Well, there are an awful lot of variants. One thing is the environment in which they're kept. If you keep a painting in a very stable environment, it will reach equilibrium with even, on paper, quite poor conditions. The reason for the drying cracks is really the materials they used, and it's often the proportion of dryers and drying oil, and also the layer structure. So the traditional way of painting is fat over lean. You want your lower layers to dry before you put your upper layers on. What you find is if you do it the other way round, the lower layers are still drying while the upper layer forms a film, and then you'll often find one pulls the other apart. So a very common reason why British 19th century and 18th century paintings cracked was the addition of asphaltum or bitumen, which doesn't dry. And it was so common in British paintings of that period, it's known as craquelé anglais by the French rather rudely, but actually their paintings aren't quite as bad as ours. And you find it in British and American pictures of this period.
Is that the same stuff that they use for pavements?
Not quite, but it is a refined tar product, and it's also in Egyptian mummies. They used asphaltum and things for the mummification process, and a pigment was made from mummified corpses in the 19th century, known as mummy brown, a very odd use of archaeological artefacts. And when Edward Burne-Jones, the Victorian painter, found what his mummy contained, he insisted on giving it a burial in the garden because he was so horrified that it had body parts in it. So that's an odd use of a non-drying component.
Can you tell me about what components go into making paint?
Well, at the simplest form, it's a mixture of a medium and a pigment. And the medium will usually be with oil paintings, a drying oil, most commonly linseed. But then people started doing things with their linseed oil to try and change its handling properties and drying properties. So they added manganese or lead dryers to speed up the drying because it's quite a slow-drying film. Or they would do things like heat body it, stand it out in the sun, or boil it to pre-polymerize it, all to change the thickness of it and to change the drying components.
So polymerization is when you have a load of small molecules and then they combine to make one long molecule. So that often makes things more viscous. And in this case, you mentioned that they did this to help them have a nice texture to paint with. So I guess causing them to polymerize would make it a bit thicker and hopefully make it dry more quickly and make it nicer to work with. Other than cracking, what else can happen to a painting over time?
Well, it can actually change in quite a few different ways. The pigments themselves can change. So sometimes they darken, more commonly they lose colour. So you'll see here at the Fitzwilliam Museum, they have a very celebrated collection of flower paintings. Quite a few of them have strangely blue-looking leaves because the yellow lake that was added to blue to make it green has disappeared. It's completely fugitive. And so what you're left is with just the blue component. So the tonal balance of the painting's completely changed. And that's normally as a result of light. And that's why the museum controls light below certain levels, both UV and lux, to try and make sure that actually that's not going to happen any more than it's happened already. You also find drying oils can become increasingly transparent. So some of the reason why sometimes you see things underneath that you weren't meant to see, like underdrawing, is the refractive index over time changes and you start to see things which once were covered. So you might see what are called pentimenti, where there are changes of mind. And the artist tried a different position for a hand or a different position for a vase or something, and you start to see them because of this change in refractive index.
And refractive index is how the light's bent when it hits a different medium. So if it's bent a lot, you'll see something different to if it's only bent a little bit. And you say that can change over time as the oils get older. Is that right?
It's part of the ageing process of painting, so this increasing transparency. So you've got various things going on. So you've got increasing transparency, but then you've got a darkening of the actual oil medium as well. So it tends to become slightly more yellow. And some artists try to compensate for this when they knew this was happening by painting paler, hoping that over time they would darken down.
Sally Woodcock from the Hamilton Kerr Institute in Cambridge. And you can hear a special follow-on podcast all about how painting restoration goes about and is undertaken on our website if you go to nakedscientists.com/specials. And still with us is Oliver Carrow, who's the surveyor of the fabric at St Paul's Cathedral. And he was listening to that, and you've got a little thing you wanted to point out, because you've got a sort of problem of a slightly different type with one of your paintings in St Paul's.
Well, cracking on paintings can happen just because the background, what the painting is on, can give up. And here in St Paul's we have the Thornhill paintings in the dome painted on the wall, which is actually cracking very badly. I saw a week or two ago because salts are coming through the wall, driven by that enemy water. So I was sitting literally this morning 270 feet above the cathedral floor on a ledge, trying to get to grips with a painting that's cracking. Quite an anxious moment.
Just for the reassurance of people who are aiming to see this one day, are you going to succeed? I mean, can you restore that?
Yes, we will. Yes, no problem at all. But we've got to deal with the water leak first and then let it dry out.
So the church roof does need the funds.
Yes, indeed.
Now, it probably comes as no real surprise that 100-year-old oil paintings like those in the Fitzwilliam Museum might need conserving. But conservators are also finding that more modern materials like plastic are also degrading.
And we're joined by Anita Quay, who's a lecturer in conservation science from the University of Glasgow. Hello, Anita.
Hello, Chris. Hello, Ginny.
So tell us, first of all, plastic conservation, is this just a modern problem?
Well, it's quite interesting. It's been going on for about 30 or so years. In the late 80s, people were starting to notice that some plastics maybe weren't surviving quite as long as we might have expected them to. They were starting to do odd things. They were starting to crack up. They were starting to weep, which sounds a bit extreme, but they were giving out liquids. And so there's quite a concerted effort from that period on, and it's escalating now. More and more people internationally are collaborating to look into the chemical reasons to why these materials are starting to degrade.
Because, of course, we're all brought up and told plastic's really bad because if it goes into landfill, it's going to last 1 million years before it breaks down and it soils the environment and these things last forever. But actually, that isn't true. And also, by the sound of it, what you're saying, there is a lot of it about that is in need of preserving because it became so ubiquitous and people don't regard it as very important.
Absolutely. Plastics have had an absolutely fascinating and perhaps quite a remarkably long history behind them. I think most people maybe think of plastics being things like PVC, which you might associate with maybe like the 1940s and post-World War II chemical efforts from that. But it actually goes back a lot earlier. We're talking about the 1860s. We're talking about the period when arts and science really were coming together to create these new man-made materials. And the ironic thing behind that is that a lot of these early synthetic plastics, which were appearing in the Victorian period and becoming quite novel materials, were based on natural polymers. Things like cellulose in paper and in cotton were being chemically modified to create some of these early ones. People might have heard of celluloid, for example, which is cellulose nitrate. And then by the early 20th century, scientists were starting to take these plastics that you could mould, that you could make into films, and starting to make fibres from them. So the very first synthetic fibre was something called rayon, which people might be familiar with. And that's where you take the natural cellulose polymer and you break the cotton polymer down, and then you regenerate it again, and you can control the length of the polymer chains, and you can make a much better fibre from it. So we're talking about collections that people might not associate with plastics, and the materials have gone from being this novel material, first of all. By the 1940s, they're becoming a very utilitarian and very much a futuristic, look what we can do, this is the future, guys, kind of material. So then by the time we get to the 1960s, and they start to get a slightly different kind of imagery behind them. They're disposable, they're not long-lasting. So it's gone through this wave of being a novelty to being something that's disposable, and I think that's lasted with us today. And now, like you say, the environmental issues that are behind them, but they are misbehaving and they're starting to degrade. And
but chemically, what underlies that degradation? Because most people regard plastics as relatively inert or stable. So what's going on inside the plastic to make it do that?
Well, when a plastic is formulated, so these are very early ones, the cellulose nitrates, the cellulose acetates, we found through some research that we've been doing is that the actual way that you make the plastic is actually, unfortunately, it's misfortune. So when, like I say, you take the cellulose and you treat it with acids, for example, and part of the process, whether you're making cellulose nitrate or cellulose acetate, is you create a cellulose sulfate as an intermediate, and then you can control this nitration or acetylation process much more in a controlled fashion. And we found that certain levels, about 5 milligrams of sulfate remaining in the plastic per gram of plastic, is enough to indicate that that particular material is either degrading or has the potential to degrade. Then with things like the PVCs, for example, PVC, we might recognise it in our homes, in our window frames, for example. You can get UPVC window frames, and that's a very hard material. But manufacturers can add in plasticizers to make that into a PVC plastic bag, for example, which you might be familiar with as a carrier bag. So you can get these formulations where you're introducing chemicals into them, and over decades, over centuries, you're now starting to get these materials moving within the plastic. So PVCs, for example, nowadays, some of the old ones that are degrading is because the plasticizer is moving through the plastic and appearing as this sticky liquid on the surface.
Can we reverse these changes?
Good question. I think if you ask a polymer scientist, the first thing that they normally respond to is, well, why don't you just coat everything? Why don't you try and reintroduce these plasticizers again? But I think Oliver mentioned it actually about reversibility, something that when it comes to preservation of collections, we're trying to be as hands-off as possible. So we're trying to control environments, trying to control humidity and temperature, which has an impact on how these materials behave. But we're actually a little bit cautious nowadays about coating things or trying to change the material back. Certainly from a chemical point of view, once these degradation processes happen, you can't chemically change them back. The amount of energy that you need is very difficult to reintroduce. And from a conservation point of view, to start interfering with the material, starting to put another material onto it, can have devastating effects. And unfortunately, through textile conservation, we found that there was a great love of using soluble nylon as an adhesive for adhering support fabrics onto things like tapestries in the 1960s and 70s. And the nylon material at the time was very reversible and could take it back off again with a solvent, but nowadays it's polymerized and it's become hardened and it's almost irreversible to remove it. So there's a great deal of wariness about doing that kind of interventive treatment at the moment.
So is it curtains, Anita, for some things that we have in our museums? Are we going to see them disappear because we just do not have the ability to preserve these plastics because they will inexorably degrade?
Yes. I think we're getting to that point now, I think, where we're just faced with more and more things coming to our collections that we're having to make decisions, and it's a big, wide issue. Again, a mountain will be eroding, but very slowly. Some materials in our collections nowadays are doing similar changes, but they're happening over a much faster period than we can imagine. So we're going to have to start making some decisions about them, and unfortunately, I don't think we can be able to keep everything. Museums are constrained economically and have to think carefully about their collections too, but conservation we're doing our absolute best that we can in collaboration with scientists around the world.
I've got an old Tesco bag from about the 1970s, which is still intact from my loft, compared with the one I had from about a month ago, which has already degraded and fallen apart. So I would treasure it. Thank you very much, Anita. Now, if you're trying to conserve your family heirlooms, we'd like to hear how you're going about it. You can let us know by emailing studio@thenakedscientist.com. You can tweet @nakedscientists, or you can find us on Facebook. You're listening to The Naked Scientists with Ginny Smith and with me, Chris Smith.
And finally, here's Hannah Critchlow with our rather dated question of the week.
This week, we tease apart history to try and solve a puzzle that Neil and Babette MacDonald wrote in with.
Historians and archaeologists talk about ancient artefacts or structures that are so many thousands of years old. How do they date these objects? Is it just from carbon dating? And did these ancient civilizations have some sort of time and date recording system in place then as well?
So, how best to date ancient artefacts? For the answer, we turn to our very own resident expert, naked archaeologist, Diana O'Carroll.
Well, the answer is a bit of both. Sometimes archaeologists make use of the dates recorded by these civilisations, but most of the time it's better to get a carbon date to check that these timeframes are accurate. When you have a king proclaiming that his ancestor ruled for 400 years, for example, it does happen, you'll want to check this out with other evidence. Now, archaeologists use a number of tools to put dates on things they find, and they tend to fall into two categories, absolute and relative. With relative dating, dig finds are placed in order, and that can be done using stratigraphy. Stratigraphy refers to the layers of earth or mineral deposits in which remains are found, and the deeper you go, the older the layer will be. Another relative dating technique uses typology. Humans tend to go through fashions in the many things they make. Whether it's pottery, road building, house construction or metal forging, we can usually identify what period the objects we find belong to. But this is only because we already have a back catalogue with which to compare them. And it's why you'll often hear an archaeologist pull a broken, unimpressive bit of pottery out of the ground and exclaim with excitement. It's usually quite useful for dating that stratigraphic layer with.
But surely sometimes these layers get mixed. Old bits of pottery might be used for generations, or what happens when someone goes against the fashion trend? In this case, an absolute dating technique is required. Back to Diana.
Carbon dating is probably the best known chemical technique, although there are others. When organisms such as people, animals, crops and trees are alive, they're continuously exchanging carbon with their environment, and there are two main types of carbon out there. The one we're interested in is carbon-14 because it's unstable. When an organism dies, that carbon-14 starts to decay at a measurable rate. All you need to do to work out when that organism died is to see how much carbon-14 is left in proportion to the other forms of carbon. So to sum up, the Mayan civilizations did have a calendar of their own, the one that was supposed to end last year, and sometimes they were kind enough to leave dates on carvings and inscriptions about their rulers. They didn't, however, leave dates for the minutiae of daily life, and that's when we need absolute dating.
Thanks, Diana O'Carroll, for a trip through the dating world. And as Evan AU points out on the forum, there are other clever archaeological tricks, like optical dating, which examines when buried minerals were last exposed to daylight. Next, moving on to present-day city life, Jeremy Eaton wrote in with this.
Do you have a stronger immune system if you live in a big city because you are surrounded by more people and their diseases?
So, do city dwellers have a stronger immune system in the long term? Let us know your thoughts by posting on our Naked Scientists Facebook page. You can tweet at Naked Scientists. You can email studio@thenakedscientists.com, or you can join in the live debate on our forum, which is at nakedscientists.com/forum.
Hannah Critchlow, and hopefully we'll all be in good health next week, living in a city as we do. That's it for this week. Thank you very much to our guest, Anders Harkinson, Oliver Caro and Anita Kwai, and thank you also to Ginny Smith for joining me. The production this week was by Kate Lamble, and next week we're going to be catching up on the emerging infections that bug us as we go around our daily business. Do join us on The Naked Scientist, which comes to you from Cambridge University, is supported by the Wellcome Trust and the EPSRC. My name's Chris Smith, and thank you very much for listening. Goodbye.